2740. Yeah, we're back. You guys just took test 2. Now we're actually going to move into the remainder of the class. And the last concept that we worked on was the multiplexer. And with the multiplexer, it was the first time really in the class that we had an intention of designing a system with a purpose for which we basically developed that system right out. And we're going to continue basically this idea of design by looking at how do we actually do arithmetic operations and then actually convert that into basically a logic schematic, and then maybe actually be able to develop a system that actually can perform the function of adding basically 2 bits together. And there's a couple of variations to this, and we're going to start off very, very simply. We're going to talk about what we call the half adder. And it's going to take a couple of videos to actually get through this. Normally, I really wish I had multiple whiteboards for this one so we could make the entire lecture complete. However, my editing software on my Mac actually really sucks, and so I can't put together multiple videos right now in just one lecture. So we're just going to kind of roll with it and see what we get. So I'm going to start off with the idea of adding 2 bits together and basically just doing essentially binary addition. So just like with the multiplexer, we're going to go right back to the truth table, and from the truth table we're going to basically say exactly how we want that output to actually look. And so we're going to have our 2 inputs, A and B, and then the output is we're actually going to have 2 outputs. We're going to have a sum and a carry, because we know that 0 plus 0 is equal to 0 with a carry of 0. 0 plus 1 is equal to 1 with a carry of 0, but once we add 1 plus 1, then we actually get an output of 0 with a carry of 1. So anytime we actually do binary additions, we actually have 2 distinct outputs that come out of that. And so looking at the truth table, sure enough, 0 plus 0 gives us 0, combination of 0 plus 1 gives us 1, carry of 0. 1 plus 0 gives us 1 with a carry of 0, and finally 1 plus 1 gives us an output of 0 with a 1. Now remember here that I'm actually not saying the truth table actually does the addition for us. I'm saying that at these combinations we are saying that we want the output of our combinational logic to be of these values with these given forms and possibilities of A and B being inputted into the system. So first thing that we want to do, well, we have a truth table. We know it's going to produce a Boolean expression that we can actually convert into logic. So let's just go ahead and make sure it's optimized. Throw it into the K-map, okay? So 2 inputs, basically get small little K-map right here. So we get 1 and 1 at these combinations. We can't actually optimize that. They can't be grouped. So the output is essentially just going to be A bar and it with B, or with A and it with B bar. That actually looks very similar to familiar to us. In fact, actually, that is the Boolean expression for the XOR gate. So sure enough, that is actually one of the first things that we readily see, that the simple summation of 2 bits together actually can be done by an XOR gate. What about that carry though? We gotta have a carry bit from that. Well, let's look here. We throw that 1 in here because that was the only time the output went high, was when A and B were both 1. And so sure enough, can't group that with nothing but itself, so the carry is just equal to AB. Well, if we have a summation Boolean expression that converts into combinational logic, and we have a carry expression that is also convertible into combinational logic, then we can just easily draw the half adder. Here we go. Bam! There it is right there, guys. We got basically 3 AND gates here. So basically we have A bar and it with B, and then we got A and it with B bar. We take the output of those 2 AND gates and then feed that into an OR gate. And this whole thing right here, that right there is just nothing but the XOR gate and the AND OR equivalency of it. And obviously, well, if we gotta have a carry bit, then down here we just pull off A and B. There it is, right there. So this right here, guys, actually performs the effective summation of two bits together and also produces a carry bit. And so if we actually think of this, well, much of the time we're not adding just two bits together. In fact, if we go back to the first part of the class, we were adding strings of bits together. Anywhere up 8 bits, we can always take it up to 64-bit, 128-bit, doesn't matter. We're always going to be adding multiple bits together. And so instead of redrawing this combinational logic over and over and over again, we can easily just go ahead and denote it as basically a block diagram. Because if we have the block diagram, it's easier to lay out that logic in such a more simplistic form. Think about it as doing that feng shui stuff that you would do in your house in order to actually make your schematics a lot easier. If we have this repeated function, there's no reason to redraw a repeated function over and over and over and over within the schematic. We just draw the diagram once, and then we basically cascade those block diagrams. So instead of thinking about adding 64 bits, let's talk about adding two strings of 2 bits together. So A1, A0, then B1, B0. Well, that seems pretty easy. So all we would have to do is actually put 2 half adders together. Well, we would add A0 and B0 together, would produce our sum, produce a carry bit. And let's see here, B1 and A1, we add those together and produce S1 and C1. Seems pretty logical to us. That works. 0, 0 produces a sum and a carry. 0, 1 produces 1 and 0. 1, 0 produces 1 and 0. Oh, got a problem though. What happens if A0 and B0 are actually both 1? We produce 0 with a carry of 1. And that carry, if that's equal to 1 here, that's a problem. Because that 1 just hangs out, and we know that if we have 1 and 0 right here, then that 1 needs to be carried all the way up, basically to the next power of 2. So, this is a problem. Guys, we gotta go back, we gotta redevelop something else. That half adder works just fine for basically A0 and B0, but what if we have to add in the carry bit? Well, got a solution. What if we just design a new system that we could tack on right here that takes into account that carry bit? Oh, well, looks like we need to go right back to the truth table. That's exactly what we're going to do.